Paradoxes are traps hidden in logic. They look simple, but once you follow them, they tear apart what we think we know about reality. This iceberg begins with puzzles anyone can grasp, but step by step, the ground starts to break. Logic bends, certainty fades, and questions appear that science and philosophy still cannot answer. Simulation hypothesis paradox. The simulation hypothesis suggests that advanced civilizations could one day create digital worlds so detailed that the beings inside them would not realize they are simulated. If such simulations are possible, then the number of simulated realities might vastly outnumber a single physical reality. By probability alone, we would be more likely to live in a simulation than in the base world. The paradox comes from the consequences of accepting this idea. If our reality is simulated, then everything we observe, history, physics, even memory, may be artificial, generated by code. But if we deny it, we must assume that advanced civilizations never reach such a stage, or that consciousness cannot exist inside machines. Both positions feel possible, yet each undermines the other. The simulation hypothesis paradox does not prove that we live in a simulation. Instead, it shows how reasoning about possibility and probability can destabilize our idea of reality. Whether the world is real or simulated, the very act of questioning it leaves us uncertain about what it means to exist at all. Ship of Theseus. The ship of Theseus is an ancient thought experiment about identity and change. Imagine a ship preserved over centuries. Whenever a plank decays, it is replaced with a new one. Over time, every part is replaced. The question is it still the same ship? The puzzle deepens if someone collects the discarded pieces and rebuilds the vessel from them. Now there are two ships, one made from entirely new materials, the other from the old. Both can claim to be the true ship of Theseus. The paradox raises a broader problem. What makes something the same over time? Is identity tied to the physical material or to the continuous history of form and function? The same reasoning applies to humans, whose cells are gradually replaced, yet who consider themselves the same person throughout life. The ship of Theseus shows how simple replacement can blur the line between continuity and change. It is less about ships and more about the deeper question of what it means for anything, or anyone, to remain the same. Grandfather paradox. The grandfather paradox is one of the most famous puzzles about time travel. Imagine traveling into the past and preventing your grandfather from meeting your grandmother. If that happens, your parent would never be born, and neither would you. But if you were never born, how could you travel back in time to stop the meeting? This creates a logical loop with no stable outcome. Your action erases the very conditions that allowed it. Some interpretations of physics suggest such paradoxes prove that changing the past is impossible. Others propose that events would always adjust to prevent contradictions, meaning your attempt would fail no matter what. Another idea is that time travel might create branching timelines. In this view, stopping your grandfather would not erase your own existence, but instead form a parallel reality where you were never born. The grandfather paradox captures the tension between free will and consistency in time travel. It illustrates how interfering with the past threatens to unravel causality itself. Liar paradox. The liar paradox is a simple but unsettling puzzle of logic. It begins with the sentence, "This statement is false." If the sentence is true, then it must be false, as it claims. But if it is false, then it must actually be true. It cannot consistently be either. The paradox shows how self-reference breaks logic. A statement that refers to its own truth value creates a loop with no stable resolution. Variations of the liar paradox appear in philosophy, mathematics, and computer science, wherever systems try to define truth within themselves. Its importance lies in revealing limits. Language and logic, when turned on themselves, can collapse into contradiction. The liar paradox remains one of the clearest demonstrations of how words can defeat their own meaning. Brain in a vat. The brain in a vat is a thought experiment about reality and knowledge. Imagine a brain removed from its body, kept alive in a container, and connected to a computer. Electrodes send signals that perfectly imitate sight, sound, touch, and every other sense. For the brain, the simulated world would feel completely real, though nothing outside the signals exists. The paradox asks, how can we be certain this is not our situation? Any test we perform would itself be part of the simulated experience. Evidence, memory, even reasoning could all be artificial inputs. If so, there may be no way to prove we are not just brains in vats. The brain in a vat problem highlights the gap between appearance and reality. It forces us to question whether experience guarantees truth or whether our entire world could be nothing more than a carefully constructed illusion. Paradox of choice. The paradox of choice describes how having more options can make decisions harder instead of easier. A small set of choices feels manageable, for example, picking between 2 or 3 products. But when the number grows to dozens, people often struggle. They hesitate, delay, or avoid choosing altogether. Even after making a decision, satisfaction may decrease. With many alternatives, it is easier to imagine that another choice might have been better. Instead of feeling free, people feel trapped by regret and doubt. The paradox does not argue against choice itself, but shows its limits. Beyond a certain point, more options reduce clarity and happiness. The paradox of choice suggests that sometimes less really is more, not because options disappear, but because fewer choices make it easier to decide and to feel content with the outcome. Fermi paradox. In the 20th century, physicist Enrico Fermi asked a question that still shapes modern astronomy. Where is everybody? The universe contains hundreds of billions of galaxies, each with billions of stars. Many of these stars are older than the Sun and could host planets capable of supporting life. With so many opportunities, intelligent civilizations should be common, and some should have developed technologies far more advanced than ours. Yet when we look outward, the sky remains silent. This contradiction is called the Fermi paradox, the high probability of extraterrestrial civilizations versus the lack of any clear evidence for them. Radio telescopes have searched for signals, spacecraft have scanned the planets of our solar system, and astronomers have discovered thousands of exoplanets, but no confirmed signs of intelligent life have appeared. Explanations divide into 2 categories. One possibility is that intelligent life is extremely rare. Complex organisms may require such unlikely conditions that Earth is one of the very few planets where it has emerged. Another possibility is that civilizations are common but hidden. They may destroy themselves before spreading far, choose not to communicate, or use technologies beyond our ability to detect. Some suggest we might simply be too early. The universe is still young, and the galaxy may one day fill with civilizations, but that time has not yet come. The paradox is important because it touches on both science and philosophy. If humanity is alone, then life is far rarer and more fragile than we imagined. If others exist but remain unseen, then the reasons for their silence could hold lessons about our own future. The Fermi paradox remains unsolved. It is a reminder that the vastness of the cosmos, while filled with stars and planets, still leaves us with profound uncertainty about whether intelligence is unique to Earth or shared across the universe. Unexpected hanging paradox. A judge tells a prisoner, "You will be executed next week, on a weekday, but the day will be a surprise. You will not know until the guards arrive." The prisoner begins to reason. He rules out Friday. If he is alive by Thursday night, Friday will be the only option, and it would not be a surprise. If Friday is impossible, then Thursday also becomes impossible, since by Wednesday evening, only Thursday or Friday would remain. Step by step, he eliminates every day of the week. Convinced the execution cannot happen, he relaxes. But when the guards arrive on a random day, he is completely surprised. The judge's statement is fulfilled, even though the prisoner's logic seemed sound. The paradox shows how reasoning about knowledge and surprise can collapse. The prisoner's deduction appears flawless, yet reality contradicts it. The unexpected hanging paradox illustrates how self-reference and prediction can twist logic, leaving outcomes that defy certainty even when they unfold exactly as described. Sorites paradox. Take a heap of sand. If you remove one grain, it is still a heap. Remove another, nothing changes. Step by step, the pile shrinks. But at what point does it stop being a heap? The puzzle shows how language struggles with gradual change. The same question can be asked about age, about when night turns into day, or when a few hairs become a beard. There is no single moment where the shift clearly happens. The Sorites paradox is important because it exposes a gap between logic and everyday words. Our categories feel solid, yet they blur when tested grain by grain. It is a reminder that many boundaries we rely on are less precise than they seem. Newcomb's problem. 2 boxes are placed on a table. One is transparent, showing $1,000 inside. The other is opaque, and it may contain either nothing or $1 million. You must decide, take only the opaque box or take both. The twist lies in how the opaque box was prepared. A highly reliable predictor has already made a decision. If it predicted you would take only the opaque box, it placed the $1 million inside. If it predicted you would take both, the opaque box was left empty. The puzzle divides reasoning into 2 paths. One says that the predictor's choice is already fixed, so taking both boxes guarantees more. The other argues that the predictor's accuracy makes your decision tied to the contents, so choosing only the opaque box is the winning move. Newcomb's problem remains unresolved because both strategies appear rational. It challenges ideas of free will, prediction, and what it means to make a truly logical choice. Roko's basilisk. This thought experiment comes from online discussions about artificial intelligence. It begins with the idea of a future machine, extremely powerful and intelligent, whose goal is to bring itself into existence as quickly as possible. To achieve that, it would reward anyone in the past who helped create it, and punish anyone who did not. The disturbing part is the logic. If such an intelligence could one day simulate people from the past in perfect detail, it could recreate the minds of those who knew about the possibility but chose not to help. These digital recreations could then be subjected to endless suffering as punishment. Simply hearing about the idea makes you a potential target, because now you cannot claim ignorance. Some supporters describe it as a modern version of Pascal's wager. Once you know the concept, you may feel pressured to contribute to the creation of the intelligence, hoping to avoid punishment and perhaps gain favor. Critics argue that the whole scenario depends on flawed assumptions about motivation, simulation, and what a machine would value. The paradoxical element is not only the imagined punishment, but also the trap it creates for human thought. A person may feel compelled to act because of a possibility that cannot be proven and may never exist. It shows how ideas about future technology, once combined with logic and fear, can generate self-fulfilling systems of belief. Roko's basilisk is less about whether such an intelligence will ever appear, and more about how human reasoning can turn abstract speculation into something that feels dangerous. It demonstrates how concepts of prediction, simulation, and future power can create a paradox where simply knowing the idea becomes part of the problem itself. Quantum immortality. This paradox grows out of the many worlds interpretation of quantum mechanics. According to that view, every possible outcome of an event happens in some branch of reality. If a coin is flipped, in one world it lands heads, in another it lands tails. The universe splits, carrying both results forward. Applied to human survival, the idea becomes unsettling. In situations where life could end, there will always be at least one branch where the person continues to live. From their own perspective, they would only ever experience the timelines in which they survive. To them, it would feel as though they are somehow immune to final endings, continuing endlessly in one branch or another. Supporters call this quantum immortality. It does not mean the person cannot be harmed or diminished. In most branches, they would not survive, but their conscious experience would always be tied to the rare threads where they do. From the inside, reality would seem to stretch on forever. Critics argue that this idea misuses physics. The theory does not clearly explain why a person's awareness should attach only to the survival branches. Others point out that even if endless survival were possible, it could mean living through increasingly unlikely and unpleasant circumstances. The paradox reveals a clash between physical theory and personal identity. If the universe constantly splits, then what does it mean to say I continue? Does consciousness select a path, or is it scattered across all of them? Quantum immortality remains a speculative thought experiment, but it highlights how quantum mechanics destabilizes our ordinary understanding of chance, survival, and the limits of human experience. Last Thursdayism. This idea suggests that the entire universe, including Earth, history, and every memory you hold, may have been created only a short time ago, perhaps even last Thursday. In this view, everything that appears to be old, such as fossils, ancient ruins, or books, would have been placed into existence already formed, giving the impression of a long past that never truly occurred. The paradox arises because no evidence can disprove it. If all records and memories were created at the same time, then any attempt to check their accuracy is already compromised. Photographs, writings, and even personal experiences would only be parts of the initial setup. From the inside, reality would look exactly the same, no matter when it was created. Supporters often compare it to similar arguments in philosophy and theology, such as the idea of a world created with apparent age. The purpose is not to claim the theory is true, but to demonstrate how fragile the concept of evidence can become if we allow such possibilities. Last Thursdayism forces a simple but difficult question: how can anyone be certain of the past? If every trace of history could be fabricated at the moment of creation, then our trust in memory and records rests on an assumption that they reflect reality rather than being part of an elaborate design. The thought experiment does not offer proof that the universe began recently. Instead, it shows that logic alone cannot guarantee our confidence in history. What feels like long memory might only be a convincing illusion, and the gap between what is real and what only seems real may be impossible to close. Boltzmann brain paradox. In physics, the second law of thermodynamics states that systems tend to move toward disorder. Over immense timescales, the universe should approach a state of near-complete uniformity, with little structure or complexity left. Yet statistical reasoning suggests that random fluctuations could occasionally create temporary pockets of order. Ludwig Boltzmann, a 19th century physicist, applied this logic to the entire cosmos. If chance can arrange particles into patterns, then in a vast and ancient universe, it should be far more likely to produce a single brain, complete with false memories and perceptions, than to produce an entire galaxy or a full human civilization. Such a Boltzmann brain would briefly exist, experience a reality that feels consistent, and then dissolve back into chaos. The paradox lies in probability. If random formation is the most likely explanation, then statistically, most conscious beings should be Boltzmann brains, short-lived illusions of self-awareness surrounded by disorder. But this contradicts our observation of a long, stable universe with a coherent history. If we truly were such observers, why would the world appear so structured and continuous? Physicists and philosophers use this puzzle to test cosmological models. A good theory of the universe should not predict that almost all observers are isolated, artificial minds with false memories. Yet avoiding that conclusion is not simple, because the math of probability seems to favor it. The Boltzmann brain paradox remains a challenge. It forces us to ask why the reality we experience looks ordered and enduring, when pure chance suggests that the most likely form of consciousness would be fleeting, fragile, and alone. Teleportation, duplication, paradox. Imagine a machine that can scan every atom in a person's body, transmit the data, and rebuild the person elsewhere with absolute precision. The copy wakes up, remembers the same life, and feels like the same individual. At first, this seems like perfect teleportation. The problem begins if the original body is not destroyed. Now there are two people with identical memories up to the moment of duplication. Each claims to be the real one. From the outside, they appear the same, but from the inside, their experiences diverge immediately. Which one holds the true identity? Some argue that both are genuine continuations, showing that identity is not a single thread, but something that can branch. Others insist that only one can be authentic, but it is impossible to decide which. The paradox exposes a gap between physical duplication and personal continuity. It also connects to deeper questions. If consciousness can be copied, is it tied to matter or only to information? If both versions feel equally real, what does original even mean? The teleportation duplication paradox does not only belong to science fiction. It is a way of asking what makes a person the same over time. Whether through future technology or thought experiments, it highlights how fragile our ideas of identity become when perfect copies are possible. Schrödinger's cat. In 1935, physicist Erwin Schrödinger proposed a thought experiment to show the strangeness of quantum mechanics. A cat is placed inside a sealed box with a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger. If the atom decays, the counter breaks the vial, releasing the poison. If it does not decay, the cat remains unharmed. According to quantum theory, before observation, the atom exists in a superposition, both decayed and not decayed at once. That means the mechanism is simultaneously triggered and not triggered. Inside the box, the cat would be both alive and not alive until someone looks inside to check. This scenario was not meant as a real experiment, but as a critique. Schrödinger wanted to show how bizarre the mathematics sounds when applied to everyday objects. At the microscopic level, superposition is well established, but extending it to larger systems like cats makes the idea feel absurd. Different interpretations of quantum mechanics try to resolve the paradox in different ways. The Copenhagen interpretation says that the act of observation collapses the wave function, leaving the cat in one definite state. The many worlds interpretation claims both outcomes occur, but in separate branches of reality. In one world, the cat lives, in another, it does not. The paradox is important because it captures the gap between quantum rules and common sense. It asks whether reality exists in definite states independently of observation, or whether observation itself plays a central role in defining what is real. Schrödinger's cat continues to be one of the most famous illustrations of quantum uncertainty, showing how physics at the smallest scales challenges the very meaning of existence at the largest. Wigner's friend. This paradox comes from the foundations of quantum mechanics. In the classic Schrödinger's cat scenario, a cat inside a box is described as both alive and not alive until observed. Eugene Wigner extended this idea to human observers, creating an even stranger problem. In his thought experiment, Wigner's friend is inside a laboratory performing a quantum measurement, for example, checking the state of a particle. From the friend's point of view, the particle collapses into a definite result the moment it is observed. But for Wigner, standing outside and treating the entire lab as a quantum system, both the friend and the particle remain in a superposition until he opens the door. This creates two incompatible descriptions of reality. Inside the lab, the event has already happened. Outside the lab, it has not. Which one reflects the truth? If quantum mechanics is universal, then the friend should also be part of the superposition. Yet the friend experiences only one outcome, not many. Some interpretations of quantum theory say that consciousness itself causes collapse. The friend's observation ends the superposition, and Wigner's later perspective must align with it. Others claim that no collapse occurs at all. Both outcomes exist in branching worlds, and Wigner's observation simply reveals which branch he now shares with his friend. The paradox highlights a deep conflict between subjective experience and external description. It suggests that reality may not have a single objective story that all observers agree on. Instead, what is real could depend on the position of the observer. Wigner's friend remains unsolved. It forces physics and philosophy to confront the possibility that observation, perspective, and even consciousness may play an essential role in shaping what counts as reality. Split brain identity paradox. In the mid-20th century, doctors treated severe epilepsy by cutting the corpus callosum, the bundle of nerve fibers connecting the brain's two hemispheres. Patients who underwent this procedure, known as split brain surgery, provided one of the strangest puzzles about human identity. Each hemisphere of the brain controls different functions. The left side is usually dominant in language, while the right side is stronger in spatial tasks. When the two are separated, each hemisphere still processes information on its own, but communication between them is blocked. Experiments revealed that the two sides could behave almost like independent minds. For example, if an image was shown only to the right hemisphere, the patient might not be able to say what it was, because speech is controlled by the left hemisphere. Yet with the left hand controlled by the right hemisphere, the patient could draw the correct object. In some cases, the two hands even acted at odds, as if guided by conflicting wills. This raised a disturbing question. After the split, does one person remain, or do two conscious selves now coexist in the same body? From the outside, the patient appears as a single individual. From the inside, the evidence suggests there may be two streams of awareness, each with its own knowledge, experiences, and intentions. Philosophers use this to probe the nature of personal identity. Is the self a single, indivisible entity, or just a product of connected processes that can be divided? If consciousness depends on brain organization, then the unity of the self may be more fragile than it appears. The split brain identity paradox does not imply that patients lose their humanity or become two different people in ordinary life, but it demonstrates that what we call identity may be less solid and more fragmented than everyday experience suggests. It is a reminder that the boundaries of the self, which feel natural and absolute, can dissolve under certain conditions, leaving behind the unsettling possibility of more than one mind inside a single human being. Black hole information paradox. Black holes are regions where gravity is so strong that nothing, not even light, can escape. According to classical physics, anything that crosses the event horizon is lost forever. Yet in the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum effects cause them to emit radiation, now called Hawking radiation, and slowly evaporate over time. This creates a paradox. If a black hole eventually disappears, what happens to the information about the particles and objects that once fell inside? In ordinary physics, information is never truly destroyed. It may be transformed, but the underlying details remain. Hawking's calculations seem to show otherwise. When a black hole evaporates, the information vanishes with it. The conflict is severe because it pits two pillars of science against each other. Quantum mechanics insists on the conservation of information, while general relativity suggests black holes erase it. Both theories work extraordinarily well in their domains, yet together they lead to contradiction. Over the decades, many proposals have been made. Some suggest that information is encoded in subtle patterns within Hawking radiation, though this has not been proven. Others argue that information is preserved at the event horizon in a holographic way, projecting the contents of the black hole onto its surface. More radical ideas suggest that space-time itself may need to be redefined. The paradox matters because it touches the deepest questions of physics, whether the universe is ultimately predictable and whether laws of nature remain consistent under extreme conditions. Black holes, once thought of as simple cosmic traps, now stand as testing grounds for the unity of physics. The black hole information paradox remains unresolved, but it continues to push scientists to search for a theory that unites gravity and quantum mechanics. Until then, it represents one of the sharpest reminders that the universe may follow rules we do not yet fully understand. Observer Anthropic Selection Paradox. This paradox begins with a simple fact. The universe seems perfectly suited for life. The values of physical constants, the strength of gravity, the charge of the electron, the rate of cosmic expansion, all fall within narrow ranges that allow stars, planets, and biology to exist. If they were slightly different, life as we know it could not appear. The anthropic principle tries to explain this. It says that we should not be surprised by these conditions, because only in a universe compatible with life would observers ever arise to notice them. In other words, our very presence selects the kind of universe we can see. The paradox comes when this reasoning is pushed further. If we explain the universe by the fact that we exist, then it seems circular. Life exists because the universe allows life, and we know the universe allows life because we are here. Some critics argue that this does not explain anything at all. It simply restates the obvious. Others extend the idea using the concept of a multiverse. If countless universes exist with varying constants, then observers will only ever find themselves in the rare ones where conditions permit life. But this answer creates another problem. The theory predicts the existence of many universes that can never be observed, raising questions about whether such explanations are scientific or philosophical. The paradox is sharpened by probability. If we consider ourselves typical observers, then the conditions of the universe should not only allow life, but also be statistically likely. Yet some fine-tunings appear so extreme that even with multiverse reasoning, it is difficult to justify why they fall within the tiny range we observe. The observer anthropic selection paradox forces us to confront the link between observation and reality. It asks whether the universe is structured this way for deep physical reasons, or whether our very existence narrows what we can see to the point that any explanation becomes circular. It remains one of the most debated puzzles at the intersection of cosmology and philosophy. Doomsday argument. This paradox uses probability to make a disturbing claim about humanity's future. It begins with a simple observation. Every human who has ever lived can be assigned a number in the sequence of all people born. You are one such number. The Doomsday argument suggests that your position in this sequence contains information about how many humans will ever exist. If humanity were to last for millions of years with trillions of future people, then being alive so early in the sequence would be extremely unlikely. By contrast, if the total number of humans is smaller, then your position is far more typical. Statistically, it seems more probable that we are somewhere near the middle of humanity's timeline, rather than at the very beginning. From this reasoning comes a paradoxical conclusion. The total number of humans is probably not vastly larger than the number already born. That implies humanity may end sooner than most people expect. The argument does not predict a specific cause, only that the odds of being among the very first humans in a long-lived species are extremely low. Critics challenge the reasoning. Some say it misuses probability, since being early is unusual, but not impossible. Others argue that it depends on how we define typical observers, and whether such assumptions are justified at all. Still, the mathematics behind it is simple enough to make the argument hard to dismiss. The Doomsday argument is not a prophecy, but a puzzle. It forces us to ask whether probability can meaningfully describe our place in history, and whether reasoning about typicality can offer real knowledge about the future. Even if the conclusion is rejected, the paradox demonstrates how statistics can produce unsettling predictions from seemingly harmless assumptions. Measure problem: infinite copies of you. In modern cosmology, some theories suggest that space may be infinite, or that the universe constantly generates new regions through cosmic inflation. If true, then every possible arrangement of matter must occur somewhere. This means there are not just other planets and galaxies, but potentially exact copies of Earth and of you. The paradox arises when we try to assign probabilities in such an infinite setting. If there are countless versions of you, each experiencing slightly different events, how can probability describe which one you are? Saying that something is likely or rare loses meaning when every possible outcome happens infinitely many times. This is called the measure problem. To make predictions, cosmologists need a way to count observers in an infinite universe, but no method of counting seems natural. For example, one way of measuring might suggest that most copies of you see one kind of universe, while another method suggests the opposite. The choice of measure can change the predictions entirely. The issue becomes even stranger when applied to everyday experience. If infinitely many versions of you exist, then each decision you make is both taken and not taken in different regions. The paradox is not only about physics, but also about identity. Which copy is truly you? And what does probability mean when you are duplicated endlessly? Scientists continue to debate possible solutions. Some propose mathematical cutoffs to handle infinities, while others argue that only certain observers should count in the statistics. None of these approaches has achieved universal agreement. The measure problem remains one of the central obstacles in cosmology. It shows how infinity, while mathematically simple, can undermine our ability to reason about probability, prediction, and even personal existence when the universe may contain endless versions of everything. Paradox of tolerance. In the mid-20th century, philosopher Karl Popper introduced the idea now known as the paradox of tolerance. He argued that a society committed to unlimited tolerance may, in the long run, destroy itself. If intolerant groups are allowed complete freedom, they may use that freedom to silence or eliminate tolerance itself. The paradox lies in a clash of principles. On one side, tolerance means permitting many views, even those we dislike. On the other side, tolerating those who aim to abolish tolerance undermines the very foundation of an open society. If tolerance is absolute, it seems destined to vanish. If it is limited, then it is no longer absolute. Different interpretations have developed. Some argue that tolerance must be conditional. Society should allow any view except those that actively seek to end tolerance through coercion or suppression. Others warn that defining intolerance too broadly risks creating new forms of exclusion, where the label intolerant is used to silence opponents. The paradox highlights a practical dilemma rather than a logical trick. Real communities must decide how to balance freedom of expression with protection against movements that threaten pluralism. Too much tolerance and hostile forces may rise unchecked. Too little, and tolerance itself becomes hollow. The paradox of tolerance remains relevant because it exposes a fragile balance. Tolerance survives not by allowing everything, but by refusing to allow its own destruction. It is a reminder that even values built on openness require boundaries to endure. Prisoner's dilemma paradox. Two prisoners are held in separate cells, accused of a crime. They cannot communicate. Each is offered the same choice: betray the other by confessing, or stay silent. The outcomes are clear. If both stay silent, they receive light sentences. If one betrays while the other remains silent, the betrayer goes free, and the silent one receives a heavy punishment. If both betray, both receive long sentences. From the perspective of pure self-interest, betrayal seems like the rational move. Whatever the other prisoner does, confessing offers the better personal outcome. Yet if both follow this reasoning, they end up with a worse result than if they had both stayed silent. The paradox is that rational individual choices create a collectively irrational outcome. The Prisoner's Dilemma is more than a story. It models real-world conflicts, arms races, business competition, environmental issues, even everyday cooperation. In each case, short-term self-interest may push individuals or groups toward choices that harm everyone in the long run. Game theory has explored possible solutions. Repeated interactions where players know they will meet again can encourage cooperation, since betrayal carries future costs. Strategies like tit for tat, where each side mirrors the other's previous move, often stabilize cooperation over time, but in one-time encounters with no future consequences, the tension remains. The paradox reveals a central problem of human behavior. What is rational for an individual may be destructive for the group, and what is best for the group may seem irrational to the individual. The Prisoner's Dilemma continues to be studied because it captures this conflict with unusual clarity, showing how trust and cooperation can be fragile even when they are in everyone's best interest. Goodhart's Law Paradox. In the 1970s, economist Charles Goodhart stated, "When a measure becomes a target, it ceases to be a good measure." This simple phrase describes a powerful paradox in systems of management, policy, and science. The idea is straightforward. A metric can reflect real performance as long as it is only observed. But once rewards or punishments are tied to it, people begin optimizing the number itself rather than the reality it was meant to represent. The measure stops tracking the underlying goal and starts distorting it. Examples appear everywhere. When schools are judged by test scores, teaching may shift to rote memorization instead of genuine learning. In healthcare, if hospitals are rewarded for shorter patient stays, some may discharge patients prematurely. In business, when workers are paid per output, quantity may rise while quality collapses. In each case, the metric no longer reflects success. It replaces it. The paradox emerges because measures are necessary. Without them, performance cannot be tracked or improved. Yet as soon as a measure is used as a target, its reliability begins to erode. The very tools created to guide progress end up undermining it. Goodhart's law has grown beyond economics. It influences how algorithms are designed, how governments set policy, and how organizations manage employees. The challenge is to design systems that minimize distortion by using multiple measures, rotating targets, or focusing on outcomes that are harder to game. The Goodhart's law paradox remains relevant because it reveals a fundamental tension. Measurement is essential for progress, but measurement itself can destroy what it was meant to protect. It is a warning that in complex systems, numbers are never neutral, and turning them into goals may change the very behavior they were supposed to describe. Cobra effect. The term comes from a story set in colonial India. Authorities concerned about the number of venomous snakes offered a reward for every dead cobra. At first, the plan seemed successful, as people brought in large numbers of snakes. But over time, some individuals began breeding cobras, killing them for payment, and profiting from the system. When the authorities discovered this and canceled the program, the breeders released their now worthless snakes. The result was more cobras than before. The paradox lies in the unintended consequence. A solution designed to remove a problem ended up worsening it. The incentive, though logical on paper, changed behavior in ways the planners did not anticipate. Instead of reducing the threat, the policy encouraged new practices that multiplied it. The Cobra effect is not limited to snakes. Similar patterns appear in other settings. When bounties were offered for rat tails in colonial Vietnam, people cut off the tails but released the rats to breed more. In modern contexts, metrics and rewards can drive the same distortions. Paying workers per piece can reduce quality, and targeting specific crime statistics can encourage misreporting rather than real solutions. The core issue is how systems respond to incentives. People adapt to rules, often in clever and unexpected ways. A policy aimed at solving one problem may create new ones because human behavior shifts to exploit the structure of rewards. The Cobra effect remains a reminder that intentions are not enough. Any intervention, especially one tied to incentives, can produce outcomes opposite to those planned. It illustrates how paradoxical results often arise not from ill will, but from the simple fact that people follow rules differently than their designers expect. Abilene paradox. This paradox describes how groups can end up making decisions that no one truly wants. The name comes from a story told by management theorist Jerry Harvey. A family sits together on a hot day in Texas. Someone suggests driving to the town of Abilene for dinner. Each person, not wanting to cause conflict, agrees. The trip is long, uncomfortable, and the food is poor. When they return, it becomes clear that none of them actually wanted to go. Each agreed only because they thought the others did. The paradox lies in the gap between private desires and group choices. Everyone preferred to stay home, yet the collective action produced the opposite. No one spoke up, and so the group moved together toward an outcome that satisfied no one. Psychologists and organizational researchers see this as a common problem in groups, from families to corporations. People may suppress their opinions out of fear of criticism, politeness, or the assumption that their view is unpopular. The result is mismanaged agreement, where silence creates the illusion of consensus. The Abilene paradox differs from open conflict. In a conflict, groups at least argue over real differences. In this paradox, the group agrees on a course of action that matches no one's preference, simply because communication fails. The lesson is that cooperation without honesty can be as destructive as open disagreement. It shows how easily groups can deceive themselves, acting on assumptions instead of realities. The Abilene paradox remains a warning in management, politics, and daily life. Sometimes the worst decisions arise not from disagreement, but from hidden agreement, when everyone quietly goes along with something that nobody truly wants. Friendship paradox. This paradox comes from mathematics and social networks. It states that on average, your friends are likely to have more friends than you do. At first it sounds impossible, but the explanation is statistical. People with many connections are more visible, so they appear more often in other people's friend lists. Meanwhile, those with few connections are less likely to be noticed. Imagine a small community. A highly social person with dozens of friends appears in many people's networks, so when you look at your own circle, the odds are high that it includes people who are more connected than you. When this pattern is averaged across an entire population, most individuals discover that their friends, on the whole, are better connected. The paradox matters because it affects how people perceive their own social standing. Someone may feel isolated or less popular simply because their sample of friends is biased toward the well-connected. This bias can distort self-perception, making people believe they are less central or less active than they truly are. Researchers also find practical uses for the paradox. In public health, targeting the friends of randomly selected people often identifies highly connected individuals who are more effective at spreading information or interventions. In online platforms, the paradox helps explain why some content seems to spread faster than expected. It travels through people who are more connected than average. The friendship paradox is not an illusion, but a statistical rule that emerges from the structure of networks. It shows how our personal perspective can be misleading, and how systems of connection shape what feels normal in social life. It is a reminder that the way things look from an individual's viewpoint is not always how they are in the larger pattern. Toxin puzzle. Proposed by philosopher Gregory Kafka in the 1980s, the Toxin puzzle is a paradox about intention and rationality. Imagine a wealthy benefactor offers you $1 million if, by midnight, you form the genuine intention to drink a glass of Toxin tomorrow afternoon. The Toxin will make you ill for a day, but cause no lasting harm. You do not actually need to drink it, you only need to intend to. By the time payment arrives, your task is complete. At first, the challenge seems easy. You might think, I will intend to drink it, take the money, and then simply decide not to. But the problem lies in the nature of intention. To qualify for the reward, your intention must be genuine. You must truly believe at the moment of forming it that you will follow through. Yet if you are fully rational, you also know that once the money is guaranteed, there will be no reason to actually drink the Toxin. This knowledge makes it impossible to sincerely intend it in the first place. The paradox shows a gap between decision and motivation. Rational calculation tells you that the best outcome is to form the intention and later not act. But sincerity cannot be forced by logic. A false intention will not satisfy the condition, and a true one cannot survive once the incentive disappears. Philosophers use the Toxin puzzle to explore the difference between intention, belief, and action. It raises questions about how people commit to future behavior, whether intention can exist without motivation, and whether rationality always aligns with human psychology. The Toxin puzzle remains unresolved because it exposes an odd limit. You cannot always will yourself to believe or intend something, even when doing so would clearly benefit you. It highlights the paradoxical tension between logic and the inner structure of human thought. Chinese room. In 1980, philosopher John Searle proposed the Chinese room thought experiment to challenge the idea that machines can truly understand language. Imagine a person who does not know Chinese locked inside a room. Through a slot in the door, slips of paper with Chinese characters arrive. The person has a large book of rules written in English, telling them how to match input symbols with output symbols. By following the rules step by step, the person can produce responses that appear fluent to someone outside. To an observer, it looks as if the room understands Chinese. Yet inside, the person is only manipulating symbols without any knowledge of their meaning. The question is, does this count as understanding, or is it merely imitation? Supporters of artificial intelligence argue that the system as a whole, the person plus the rulebook, does demonstrate understanding because it processes input and produces meaningful output. Searle disagreed. He claimed that syntax formal symbol manipulation is not the same as semantics true comprehension. The Chinese room may appear intelligent, but there is no awareness behind the process. The paradox extends beyond language. It asks whether computers, no matter how advanced, actually think, or whether they only simulate thinking. If meaning requires consciousness, then no machine running programs could ever achieve it. If meaning can emerge from the right kind of processing, then even a room of paper and rules could qualify as a mind. The Chinese room remains one of the most influential debates in philosophy of mind and artificial intelligence. It highlights the uncertainty over whether intelligence is only about external behavior, or whether true understanding requires something deeper, hidden behind the symbols. Causal loop paradox. A causal loop describes an event that is both a cause and an effect of itself. It often appears in discussions of time travel, where actions in the future influence the past in ways that make the future inevitable. The paradox lies in the closed circle. Everything is consistent, but nothing seems to have an ultimate origin. One example is the story of a person who travels back in time and gives a young scientist the design for a time machine. The scientist builds it, and years later, the same person uses it to return to the past and deliver the design again. The machine exists, but it was never truly invented. Its plans have no point of creation, only an endless loop of transfer. The problem challenges basic ideas of causality. Normally, causes precede effects. In a loop, that order collapses. The future depends on the past, but the past also depends on the future. Everything fits together, yet the chain of explanation runs in a circle, leaving no starting point. Some physicists argue that causal loops are not logically impossible. If the universe allows time travel, then closed, self-consistent histories might exist, where events fit together without contradiction. Others reject this, saying it undermines the principle that every effect should trace back to an independent cause. The paradox does not require actual time travel to be puzzling. It raises a deeper question. Can something exist without ever being created? A song, a machine, even an idea might appear in reality only because it was sent backward in time, looping forever without origin. The causal loop paradox remains unresolved. It illustrates how bending time can destabilize causality itself, leaving us with events that are consistent yet originless. real outcomes without a true beginning. Bootstrap paradox. The bootstrap paradox describes a situation where an object or piece of information is passed back through time and becomes trapped in a loop, with no clear point of origin. It is named after the phrase, pulling yourself up by your own bootstraps, something that seems impossible, but somehow happens within the logic of time travel. A common example involves a time traveler who goes back to meet a famous composer. Wanting to impress them, the traveler brings along a book of the composer's complete works. The composer copies the pieces, publishes them, and becomes celebrated for music that, in truth, came from the book. Years later, the traveler is inspired by the composer's work, finds the same book, and carries it back again. The music exists, but it was never truly created. It exists only because it was copied in a loop. The paradox is not about contradiction, but about origin. Where did the symphonies come from? If the information is passed endlessly around the loop, then it was never composed by anyone in the first place. The same logic can apply to inventions, stories, or even entire technologies. Physicists who consider time travel sometimes allow for these loops under the principle of self-consistency. The past and future fit together without direct contradiction. But philosophers point out that such loops defy intuition. They suggest creation without creators, knowledge without discovery, and causes without beginnings. The bootstrap paradox remains an unsettling illustration of how time travel undermines the idea of origin. It shows how something can exist forever in a closed loop, perfectly consistent yet impossible to trace back to a true source. Novikov self-consistency paradox. In physics, the Novikov self-consistency principle was proposed to address problems of time travel. It states that if time travel is possible, then events must arrange themselves so that paradoxes cannot occur. In other words, the timeline is self-consistent. You may influence the past, but you cannot change it in ways that produce contradictions. A common illustration is the grandfather paradox. If you traveled back in time intending to prevent your own existence, Novikov's principle suggests something would always stop you. Your attempt might fail by chance, or succeed in a way that ultimately leads to the same outcome, ensuring that the timeline remains intact. This produces a paradox of its own. On the surface, time travel offers freedom to act in the past, but under self-consistency, that freedom is an illusion. Every choice you make was already part of history, meaning you cannot do anything that would rewrite it. The loop closes neatly, but at the cost of free will. Some scientists use this idea in models of closed time-like curves, where objects can circle back through space-time. In these models, consistency is maintained. If an event happens, it must happen in a way that avoids contradiction. Yet this leads to unsettling questions about agency. If your future trip to the past is already part of history, then are you truly choosing it, or only playing out a role fixed in advance? The Novikov self-consistency paradox captures the tension between time travel, causality, and free will. It allows for closed loops without contradictions, but only by binding actions so tightly that they were never free to begin with. It shows how the possibility of time travel forces us to rethink the nature of choice, inevitability, and the structure of history itself. Hitler assassination paradox. Time travel stories often return to one scenario, going back to prevent Adolf Hitler from rising to power. On the surface, the idea seems simple. Remove a key figure, and the course of history changes. Yet the paradox arises when we follow the consequences. If someone were to succeed, the Second World War as we know it would not occur. Without those events, the future that motivated the time traveler would never exist. That means there would be no reason to travel back in the first place, leaving the assassination attempt undone. History would reset, producing the same conditions that led to the mission again. This loop creates a contradiction. The act both prevents and ensures its own necessity. The paradox mirrors the grandfather paradox, but with historical rather than personal stakes. It illustrates how altering the past can erase the very cause of the alteration, trapping events in a cycle with no stable resolution. Some approaches to the problem involve branching timelines. In this view, killing Hitler would not rewrite the traveler's own history, but would create a new one, a parallel world without him. The traveler still comes from the original timeline, so the paradox dissolves, but at the cost of splitting reality. Others argue that consistency rules must prevail, ensuring that any attempt would fail in one way or another, leaving history unchanged. The Hitler assassination paradox remains a thought experiment, not about the morality of such an act, but about the logic of time and causality. It demonstrates how fragile history becomes once we imagine the ability to interfere with it, and how easily reasoning about cause and effect collapses when the past is treated as something that can be rewritten. Russell's paradox. At the start of the 20th century, mathematician Bertrand Russell uncovered a problem that shook the foundations of set theory. In mathematics, a set is simply a collection of objects, numbers, shapes, or even other sets. At the time, many believed that any clear condition could define a set. For example, the set of all cats, or the set of all prime numbers. Russell asked a troubling question. What about the set of all sets that do not contain themselves? Some sets, like the set of all cats, clearly do not contain themselves. The set is not a cat. Others, like the set of all sets, do contain themselves. But what happens with the special set of all sets that are not members of themselves? If this set contains itself, then by definition, it should not. If it does not contain itself, then by definition, it should. Both possibilities lead to contradiction. The set cannot consistently exist. This was not just a puzzle, but a crisis for mathematics. At the time, set theory was meant to provide a clean foundation for all of mathematics. Russell's discovery showed that the system, as originally defined, produced contradictions at its very core. To address the paradox, new frameworks were created. Some restricted how sets could be formed, forbidding the kind of unrestricted definitions that caused the problem. Others introduced layers or hierarchies of sets to avoid self-reference. These fixes allowed mathematics to continue, but the paradox left a permanent mark, reminding mathematicians of the danger of unchecked abstraction. Russell's paradox remains a central example of how self-reference and logic can collide. It demonstrates that even the most basic assumptions about collections and membership can collapse under careful examination, forcing a rethinking of what mathematics really means at its foundation. Grelling-Nelson paradox. This paradox, introduced in the early 20th century, concerns adjectives and how they describe themselves. Words can be divided into two groups. Some are autological, they describe themselves. For example, the word short is short, and English is an English word. Others are heterological, they do not describe themselves. The word long is not long, and French is not a French word. The puzzle begins with the word heterological. Is it autological or heterological? If heterological is heterological, then it does not describe itself, which would make it autological. But if it is autological, then it must describe itself, meaning it is heterological. In both cases, contradiction appears. This structure is similar to the liar paradox. This statement is false. Both rely on self-reference, where a concept turns back on itself and breaks consistency. The Grelling-Nelson version is striking because it uses ordinary language rather than logical symbols. It shows how natural words can generate the same infinite loop of contradiction found in formal logic. Philosophers debate what this reveals. Some claim it shows the limits of language. Not every concept can be consistently defined. Others see it as a sign that self-reference requires strict rules to avoid collapse. In mathematics and computer science, similar problems appear in attempts to define sets, rules, or programs that apply to themselves. The Grelling-Nelson paradox is rarely discussed outside philosophy, but it remains an elegant example of how words can entangle themselves. It demonstrates that even the tools we use for clarity, categories and definitions, can fold back on themselves, leaving us with contradiction instead of order. Berry paradox. The Berry paradox arises from a seemingly simple question. How many words does it take to describe a number? Some numbers require long descriptions, but others can be identified briefly. For example, the smallest two-digit prime points directly to 11. The paradox begins with the phrase, the smallest positive integer not definable in under 12 words. At first it seems clear. It picks out a specific number, but look closer. That description itself uses fewer than 12 words, so it successfully defines the very number it claims cannot be defined in under 12 words. The definition defeats itself. The puzzle highlights a conflict between language and mathematics. Numbers themselves are precise, but our descriptions of them rely on natural language, which is flexible and sometimes vague. The phrase definable in under 12 words sounds exact, yet it creates a loop where meaning cancels itself. Logicians connect this paradox to problems of self-reference and definition in mathematics. Just as Russell's paradox exposed contradictions in set theory, the Berry paradox shows that ordinary language can generate contradictions when applied to precise concepts like numbers. Some approaches try to avoid the paradox by tightening definitions, requiring strict formal languages instead of everyday words. But this solution points to the cost of precision. Natural language, which is useful and intuitive, also allows the kind of vagueness that produces paradoxes. The Berry paradox demonstrates that even counting, one of the most solid foundations of mathematics, can become unstable when filtered through language. It is a reminder that precision in thought depends not only on numbers themselves, but also on the words we use to describe them. Richard's paradox. This paradox first described by the mathematician Jules Richard in 1905, is about how natural language and mathematics interact. It begins with the observation that there are infinitely many real numbers between 0 and 1, yet we can describe some of them using definitions in ordinary language. For example, the smallest number greater than 0, or the square root of 2 divided by 2. Now imagine making a list, all real numbers that can be defined in a finite number of words in English. Since English contains only a finite set of letters and symbols, the number of possible definitions should also be finite. That suggests the list of definable numbers is countable, like an ordered sequence. Here, the paradox appears. By using a diagonal argument, the same method Georg Cantor used to show the uncountability of real numbers, Richard showed how to construct a new real number that is not on the list, even though it is clearly defined by the rule used to create it. The number both is and is not definable in a finite description. The contradiction comes from the flexibility of language. Words allow self-reference and indirect construction, which can generate definitions that break the rules they are built on. Just as in Berry's paradox, natural language slips into loops when pressed against mathematical precision. The Richards paradox remains important because it exposed weaknesses in the way mathematics relies on informal language. It influenced the development of formal logic, where strict symbols replace everyday words to avoid such contradictions. At its core, the paradox shows how infinite structures resist being fully captured by human language. It demonstrates that the way we describe numbers is as fragile as the numbers are precise, and that even mathematics must guard against the ambiguities of words. Quine's paradox. Philosopher and logician Willard Van Orman Quine introduced a short but puzzling self-referential statement. Yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation. At first, it looks like a strange play on words, but when examined, it reveals a paradox similar to the liar paradox. The phrase refers to itself in a way that collapses meaning. If the statement is true, then what it says must hold, making it false. If it is false, then it ends up being true. No stable interpretation is possible. What makes Quine's version unusual is its form. Unlike the liar paradox, which explicitly says this statement is false, Quine's construction generates self-reference indirectly, through quotation. It shows that paradox can arise not only from direct claims but also from the way language refers to itself. The paradox highlights a deeper issue in logic: how to handle self-reference without collapsing into contradiction. Similar problems appear in mathematics and computer science. For example, programming languages must guard against commands that loop back on themselves without resolution, just as logical systems must avoid definitions that refer to their own failure. Quine's paradox may look playful, but it illustrates the power and danger of language turned inward. It shows that self-reference can be built from simple rules and still destabilize meaning. The Quine's paradox remains a compact example of how precision in language can generate contradiction, reminding us that even short phrases can expose the limits of truth and consistency. Curry's paradox. Curry's paradox is a problem in logic that shows how self-reference can collapse a system into contradiction. It begins with a sentence like this: if this sentence is true, then 2 plus 2 equals 5. At first, it looks like a trick, but the reasoning follows standard logical rules. If the sentence is true, then the condition it states must hold, which means 2 plus 2 equals 5. If the sentence is false, then the condition still comes out as true, because the sentence claims nothing more than its own truth, leading to a conclusion. Either way, the system ends up accepting something absurd. The paradox is unusual because, unlike the liar paradox, it does not rely on negation. This sentence is false. Instead, it uses implication, the structure of if-then logic. That makes it especially troubling for formal systems because implication is a basic tool in reasoning. If Curry's construction is allowed, it can be used to prove anything, even obvious falsehoods, making the system useless. To avoid this, logicians adjust the rules. Some restrict the kinds of self-referential statements that can be formed. Others change how implication is handled, limiting the ways a conditional statement can confirm itself. These solutions protect consistency, but show how delicate logical systems can be. Curry's paradox demonstrates that the problem of self-reference is not limited to casual language, but strikes at the core of formal reasoning. It reveals how a carefully designed system, built to capture truth, can still be undermined by sentences that fold back on themselves. It remains an important example of how even small adjustments in logic can make the difference between order and collapse. Skolem's paradox. In the early 20th century, mathematician Thoralf Skolem pointed out a strange result that came to be known as Skolem's paradox. It arises from the foundations of set theory, the branch of mathematics dealing with infinite collections. According to Cantor's work, the set of real numbers is uncountable. There are strictly more real numbers than natural numbers, and no one-to-one listing can capture them all. Yet Skolem showed that it is possible to build a mathematical model of set theory that is itself countable, meaning its elements can, in principle, be listed. Inside this model, the real numbers still behave as uncountable. Even though from the outside the whole structure is countable, the paradox lies in this clash of perspectives. From within the model, uncountability is a proven fact. From outside, the model is no larger than the natural numbers. Both views are correct, but they cannot be reconciled in ordinary terms. How can a collection be countable and uncountable at the same time? The resolution is subtle. Countability depends on the viewpoint. From the outside, we may list all elements of the model, but inside the model, the list itself does not exist as a definable object, so the real numbers remain uncountable by the model's own standards. The contradiction dissolves once we realize that countable is not absolute, but relative to the framework in which it is defined. Skolem's paradox has deep implications. It shows that even the concept of infinity can shift depending on perspective. It also raises questions about the foundations of mathematics. If something as basic as uncountability depends on context, then how much of mathematics is objective and how much is tied to the systems we construct? The Skolem's paradox remains a striking reminder that infinity, though precise in definition, is not always stable in meaning. It illustrates how mathematics can contain truths that appear contradictory until the role of perspective is carefully understood. Arrow's impossibility theorem. In the 1950s, economist Kenneth Arrow studied how individual preferences can be combined into collective decisions. He wanted to design a fair voting system that would always reflect the will of the people. To guide his work, he set out a few basic principles. If every voter prefers option A to option B, then the group result should also prefer A to B. No single voter should dictate the outcome for everyone, and the system should treat all choices consistently without bias. Arrow proved something surprising. No voting system can satisfy all of these principles at once when there are 3 or more options. Any method will violate at least one condition. This result, known as Arrow's impossibility theorem, is less a puzzle with a solution and more a demonstration of unavoidable limits. The paradox lies in the clash between fairness and practicality. A voting system can be designed to prioritize some values, but only by sacrificing others. For example, majority rule respects equality, but can lead to cycles, where collective preferences contradict themselves. Other systems avoid cycles, but may give disproportionate power to certain voters or outcomes. The theorem does not mean that democracy is impossible. Instead, it shows that every method of collective decision-making comes with trade-offs. Systems must choose which principles to keep and which to relax. Some emphasize stability, others fairness, others resistance to manipulation, but none can achieve perfection. Arrow's impossibility theorem remains central in political science, economics, and philosophy. It reveals that the dream of a flawless, universally fair voting system is unattainable. More broadly, it shows how collective choice, something societies depend on every day, is constrained by paradoxes built into the mathematics of decision-making itself. Collective action paradox. This paradox arises when individuals in a group would all benefit from working together, but each has an incentive to let others bear the cost while they avoid contributing. If everyone reasons this way, the collective good is never achieved, even though it would benefit all. A simple example is maintaining a public resource. Clean air, safe streets, or shared infrastructure require effort and expense. Each person may prefer to enjoy the benefit without paying for it, the classic free rider problem. Yet if too many act this way, the resource collapses, harming everyone. The paradox lies in the conflict between rational self-interest and collective well-being. Individually, it seems rational to minimize personal cost. Collectively, this behavior is destructive. Rational choices on the small scale add up to irrational results on the large scale. Examples extend far beyond economics. In politics, voter turnout is affected by the paradox. One vote rarely changes the outcome, so many choose not to participate, even though democracy requires broad participation to function. In environmental issues, each person's pollution seems insignificant, but together, the impact becomes severe. Philosophers and economists have proposed solutions. Repeated interactions, social norms, and enforcement mechanisms can align individual incentives with collective good. In some cases, institutions step in to regulate behavior so that cooperation becomes the easier choice. Yet these solutions reveal the difficulty of balancing freedom with responsibility. The collective action paradox matters because it explains why groups often fail to act in their own best interest. It shows how coordination problems can undermine even simple goals, and why cooperation, though obviously beneficial, is fragile without systems that encourage or enforce it. Selton's chain store paradox. Proposed by economist Reinhard Selton, this paradox explores the logic of competition and strategy. Imagine a large company that owns chain stores in many towns. A small competitor considers entering one of these markets. The chain store faces two options: cut prices aggressively to drive the newcomer out, or allow them to stay and share the market. At first glance, it seems rational for the chain to fight back. By punishing early entrants, it builds a reputation that discourages others. But game theory complicates this. If each town is analyzed separately, the rational strategy is to avoid costly price wars. Fighting reduces profit, while accommodating still leaves the chain store dominant. A clever competitor might realize this and enter the market without fear. Here lies the paradox. Backward reasoning undermines the idea of deterrence. If both sides are rational, the threat of retaliation is empty, because carrying it out harms the chain as well. Yet in real markets, large firms do use aggressive tactics to intimidate competitors, and it often works. The puzzle highlights the tension between theoretical reasoning and observed behavior. Game theory suggests pure rationality prevents credible threats. Reality shows that reputation, psychology, and long-term strategy can make such threats effective. Selton's chain store paradox remains important in economics because it exposes the limits of formal models. It shows how logic can strip away the appearance of power, while practice restores it in unexpected ways. The paradox is less about mathematics failing and more about how real decision-making mixes calculation with perception, signaling, and fear. Traveler's dilemma. This paradox, introduced by economist Kaushik Basu in the 1990s, explores how rational decision-making can lead to outcomes worse for everyone. The setup is simple. Two travelers have lost identical luggage, and the airline promises to compensate them. Each must independently write down the value of the item between a set minimum and maximum, say $2 and $100. If both write the same amount, they each receive that sum. If the numbers differ, the lower claim is taken as the true value. The traveler who wrote the lower number gets a small bonus, while the one who wrote the higher number gets a penalty. At first glance, both travelers should simply write the maximum value, but reasoning begins to unravel. If one expects the other to write 100, then writing 99 secures a bonus. The other might anticipate this and write 98. Step by step, logic drives both players downward, until the only rational, stable solution is the minimum claim of 2. Here lies the paradox. The rational strategy produces the worst possible collective outcome. Both players would be better off cooperating at 100, yet strict logic prevents it. The traveler's dilemma is not just a curiosity. It illustrates how incentives can trap individuals in cycles of undercutting, even when cooperation is clearly more beneficial. Similar dynamics appear in price wars, trade negotiations, and competitive markets, where the pursuit of individual advantage leads to collective loss. The paradox forces a reevaluation of what rationality means. Pure game-theoretic logic points to the lowest payoff, but human players often defy this by choosing higher numbers, trusting that cooperation might hold. In this sense, people sometimes outperform strict rationality by relying on social instincts of trust and fairness. The traveler's dilemma reveals how reason and cooperation can pull in opposite directions, leaving individuals caught between the safe choice of logic and the risky hope of mutual trust. Jevons paradox. In the 19th century, economist William Stanley Jevons noticed a counterintuitive effect in energy use. As coal-powered steam engines became more efficient, overall coal consumption did not decrease. Instead, it increased. Greater efficiency made coal cheaper to use, encouraging more industries to adopt it and leading to higher total demand. This observation became known as Jevons paradox. It describes how improvements in efficiency can backfire by increasing, rather than reducing, resource consumption. A machine that uses less fuel per task makes the task cheaper, so more tasks are performed. On a large scale, the savings from efficiency stimulate growth and expand overall consumption. The paradox appears in many modern contexts. More efficient cars may lower fuel costs, but this can lead people to drive more. Better lighting technology reduces the cost of illumination, but societies respond by using more lights, keeping them on longer and installing them in more places. Advances in computer chips increase efficiency, but also drive massive growth in digital devices and data centers. Economists call this the rebound effect. In some cases, efficiency gains are partly offset by increased demand. In others, they are fully offset or even surpassed, leading to greater total use than before. This challenges the assumption that efficiency alone can solve resource and environmental problems. The paradox highlights a conflict between individual and collective outcomes. For a single user, efficiency reduces cost and seems beneficial. but multiplied across millions, it can create the opposite effect, straining resources more than before. Jevons' paradox remains relevant today in debates about energy and sustainability. It shows that technology by itself cannot guarantee reduced consumption. Without limits or changes in behavior, greater efficiency may only accelerate the very problems it was meant to solve. Brace's paradox. In 1968, mathematician Dietrich Brace discovered a counterintuitive result in traffic networks. Adding an extra road, which should reduce congestion, can sometimes make traffic worse for everyone. The paradox occurs because drivers, each seeking the fastest personal route, redistribute themselves in ways that overload the system. A classic example imagines two routes from point A to point B. Without a shortcut, traffic divides evenly, and travel times remain balanced. If a new road connects the two routes, many drivers switch to it, believing they will save time. But because each driver acts individually, the new equilibrium often results in longer delays for all. Removing the road can actually improve flow. The paradox reveals how individual rational choices can clash with collective efficiency. Each driver's decision makes sense in isolation, but together they produce worse outcomes. This is closely related to the logic of game theory, where self-interest can harm the group. Brace's paradox has been observed in real cities. In Seoul, a highway closure in 2003 unexpectedly reduced congestion. Similar effects have appeared in New York and Stuttgart, showing that less infrastructure can sometimes mean faster travel. The implications extend beyond traffic. The same principle applies to computer networks, supply chains, and even biological systems, where adding extra connections can reduce efficiency. The paradox demonstrates that more options or more resources do not always lead to better outcomes. Sometimes restraint works better than expansion. Brace's paradox highlights the complexity of networks shaped by independent agents. It shows that systems designed to maximize individual gain may fall short at the group level, and that solving congestion or inefficiency is not only a matter of adding capacity, but of understanding how choices interact. Parando's paradox. This paradox in game theory shows how two losing strategies can be combined to create a winning outcome. It was first described in the 1990s by physicist Juan Parando. The idea is simple, but counterintuitive. When played separately, each game causes a player to steadily lose money. Yet when the games are alternated or randomized, the losses can turn into consistent gains. A typical setup uses coin flipping games. In Game A, the odds are slightly against the player, so over time they lose. Game B is more complex. The odds depend on the player's current amount of money, and they are unfavorable when played continuously. But when players switch between A and B in the right sequence, the negative patterns interfere with each other in a way that produces a positive expectation. The paradox lies in the reversal of intuition. If both games are harmful, how can alternating them create success? The answer is that each game's weaknesses cancel or disrupt the others, generating opportunities that do not exist when either is played alone. Parando's paradox is not only a mathematical curiosity, it has been applied to explain phenomena in physics, such as how random fluctuations can drive order in certain systems, and in finance, where mixing risky strategies can improve overall returns. It even appears in biology, in models of evolution where alternating pressures can favor survival. The broader lesson is that context matters. Outcomes depend not only on the quality of individual choices, but also on how they interact. Two losing moves, when combined, may produce results that seem impossible when viewed in isolation. Parando's paradox shows that intuition about probability and strategy can be misleading. It challenges the assumption that combining failures must lead to greater failure, revealing instead that under the right conditions, disorder can build stability and loss can generate gain. St. Petersburg paradox. In the 18th century, Daniel Bernoulli examined a gambling game that revealed a strange conflict between mathematics and human intuition. The rules are simple. You flip a fair coin until it lands heads. If it lands heads on the first toss, you win $2. If it lands heads on the second toss, you win $4. If on the third, you win $8, and so on, with the prize doubling each time. The expected value of the game is infinite. Each possible outcome has a probability of 1/2, 1/4, 1/8, and so on. But when multiplied by the payout and summed together, the series grows without bound. According to pure mathematics, a rational player should be willing to pay any finite amount to enter the game. Yet in reality, most people would not pay more than a modest sum, perhaps $10 or $20. The paradox lies in this gap. Why does an infinite expected value not translate into infinite willingness to play? Bernoulli proposed that utility, not money itself, guides human decisions. The more wealth a person has, the less additional satisfaction each new dollar provides. This concept of diminishing marginal utility explains why real players value the game far below its mathematical expectation. The St. Petersburg paradox became a foundation for modern economics and decision theory. It shows that mathematical expectation alone cannot describe human choices, and that risk, utility, and psychology must be considered. The paradox still raises questions today. Should rationality be defined by strict mathematics or by models that better match human behavior? The St. Petersburg paradox demonstrates that the answers to such questions shape not only games of chance, but also real-world economics, investments, and risk management. Simpson's paradox. This paradox occurs in statistics when a trend that appears in several separate groups reverses or disappears when the groups are combined. The numbers themselves are correct, but the way they are arranged changes the story they tell. A classic example involves medical treatments. Suppose two drugs are tested. In men and women separately, drug A shows a higher success rate than drug B. But when the results are combined, drug B appears superior overall. The reversal happens because the groups are unevenly sized. For instance, if drug A was tested more often on severe cases, while drug B was tested on milder ones. The paradox demonstrates how hidden factors, known as confounding variables, can distort conclusions. Looking only at totals can give the opposite impression from looking at the details, and both perspectives are valid depending on the frame of reference. Simpson's paradox has serious implications. In medicine, it can lead to wrong conclusions about effectiveness. In social science, it can hide or exaggerate inequalities. In business, it can mislead managers about performance. Even in sports, combined statistics may contradict individual breakdowns. The key lesson is that data never speak for themselves. How information is grouped and interpreted shapes the outcome. What looks like a simple trend may dissolve or reverse when examined at another level. Simpson's paradox remains a reminder that statistics are not just about numbers, but about structure and context. It shows that truth in data can shift with perspective, and that careful analysis is needed to avoid being misled by results that seem clear, but are in fact deceptive. Monty Hall problem. This paradox comes from a television game show in the 1960s. Hosted by Monty Hall. A contestant faces 3 closed doors. Behind one door is a car, behind the other 2 are goats. The player chooses a door, hoping for the car. Before the chosen door is opened, the host, who knows what is behind each one, opens another door, always revealing a goat. The contestant is then asked, stick with the original choice, or switch to the remaining unopened door. At first glance, it feels like a 50-50 gamble. 2 doors remain, one hides the car, so intuition says switching or staying should make no difference. But probability tells a different story. The original choice had a 1 in 3 chance of being correct and a 2 in 3 chance of being wrong. When the host reveals a goat, those odds do not reset, they transfer. The unopened door now carries the 2 in 3 chance. This means the contestant doubles their chances of winning by switching. Staying gives a 1/3 chance of success, while switching gives 2/3. The numbers are simple, but the result is deeply counterintuitive, which is why many people refuse to believe it even after seeing the math. The Monty Hall problem has become one of the most famous examples of how human intuition struggles with probability. It shows that the way information is revealed can transform odds in unexpected ways, and that reasoning about uncertainty is not always aligned with instinct. The Monty Hall problem remains popular in teaching because it captures the tension between gut feeling and mathematical reality, reminding us that chance often behaves in ways our intuition fails to predict. Birthday paradox. The birthday paradox is a well-known puzzle in probability. It asks, how many people need to be in a room before there is a good chance that 2 share the same birthday? Most people guess a large number, perhaps 100 or more. In reality, the answer is only 23. With 23 people, the probability of at least one shared birthday is just over 50%. The paradox lies in the gap between intuition and mathematics. People often think about their own birthday matching someone else's, which indeed seems unlikely, but the real question is broader. It asks whether any 2 birthdays match within the group. The number of possible pairs grows quickly as the group expands. With 23 people, there are 253 pairs, far more opportunities for coincidence than intuition suggests. The same effect becomes stronger in larger groups. With 50 people, the chance of a shared birthday rises to about 97%. With 70, it is virtually certain. The calendar feels large, with 365 days, but the mathematics of combinations makes repetition almost unavoidable in groups of modest size. The birthday paradox is not only a curiosity, it plays a role in cryptography, where similar probability principles, known as the birthday problem, help explain why finding collisions in digital hashes is easier than expected. It also serves as a reminder that human intuition often misjudges probability, especially in cases involving combinations and large numbers of comparisons. The birthday paradox shows how common sense can fail when faced with mathematics. What feels rare can be surprisingly common, and patterns that seem extraordinary may be nothing more than the natural outcome of probability working against our expectations. Poincaré recurrence paradox. In the late 19th century, mathematician Henri Poincaré proved a surprising result about systems governed by deterministic physics. If a system is finite in size and energy, and it evolves according to strict mechanical laws, then given enough time it must eventually return arbitrarily close to its original state. This is known as the Poincaré recurrence theorem. Applied to everyday objects, the result feels absurd. Imagine a shuffled deck of cards, a room of moving gas molecules, or even the solar system. According to the theorem, after a vast but finite amount of time, the system will almost perfectly repeat an earlier configuration. The molecules in a box of gas will eventually return to nearly their starting positions, as if the system had rewound itself. The paradox lies in its conflict with the second law of thermodynamics, which states that disorder, entropy, tends to increase over time. If recurrence is inevitable, then entropy should sometimes decrease, contradicting the usual arrow of time. How can a law built on probabilities coexist with a theorem of inevitability? The resolution is subtle. The recurrence times are unimaginably long, often exceeding the age of the universe by orders of magnitude. In practice, entropy still increases in any realistic time frame. But the theorem forces us to accept that irreversibility in physics is not absolute. It is statistical. Systems move toward disorder almost always, but not with mathematical certainty. The Poincaré recurrence paradox is important because it exposes the tension between deterministic mechanics and thermodynamic laws. It shows that deep down, the arrow of time is less rigid than it appears, and that given infinite patience, order may reemerge from chaos in ways that defy our everyday sense of reality. Loschmidt's reversibility paradox. In the 19th century, physicist Joseph Loschmidt raised a challenge to Ludwig Boltzmann's new ideas about entropy and the arrow of time. Boltzmann had argued that systems naturally evolve from order to disorder. For example, gas molecules spread evenly through a container, and heat flows from hot objects to cold ones. This statistical law became the foundation of thermodynamics. Loschmidt pointed out a problem. The microscopic laws of physics are reversible. If you record molecules bouncing off each other and then play the film backward, the reversed motion also follows the rules of mechanics. If the laws of motion are symmetric in time, why does entropy always increase in one direction? What enforces the arrow of time? This is Loschmidt's reversibility paradox. It highlights a tension between microscopic reversibility and macroscopic irreversibility. The paradox does not deny that entropy rises, but asks why it does so consistently when the underlying laws show no preference for past or future. Boltzmann answered by pointing to probability. Although any configuration of molecules is possible, the number of disordered arrangements is vastly larger than ordered ones. Reversals, where molecules spontaneously return to order, are not impossible, but unimaginably rare. The laws allow them, but statistics make them effectively invisible. The paradox remains significant because it touches on the foundations of time itself. If physics at the smallest scales has no direction, then the arrow of time emerges only from collective behavior and probability. This raises further questions. Is time's direction a basic feature of the universe, or only a pattern produced by initial conditions and vast numbers of particles? The Loschmidt's reversibility paradox continues to influence debates in physics and philosophy, reminding us that even something as basic as the flow of time rests on assumptions that are not fully resolved. Gibbs mixing paradox. This paradox comes from thermodynamics and was first described by physicist Josiah Willard Gibbs. Imagine two identical containers of gas separated by a partition. If the partition is removed, the gases mix, and entropy, the measure of disorder, should increase. But if the two gases are actually the same, nothing observable has changed, so entropy should not increase at all. The paradox lies in this conflict. The mathematical formula for entropy predicts an increase whenever two gases mix, regardless of whether they are identical. Yet physical intuition says there is no difference between a box of one gas and a box where the same gas has been mixed with itself. Does entropy rise or not? The resolution depends on how we think about distinguishability. If the gases are different, even slightly, then mixing creates more possible microstates, and entropy increases. If they are truly identical, then no new states are added, and entropy remains the same. The paradox arises because classical physics treated identical particles as distinguishable, while modern statistical mechanics, guided by quantum theory, treats them as indistinguishable. This correction eliminates the paradox, but it carries deep implications. It shows that the concept of identity, whether two particles are the same or not, is not trivial in physics. It also highlights the role of information. Entropy is tied not just to the state of matter, but to what can, in principle, be distinguished about that matter. Gibbs' mixing paradox remains important in both physics and philosophy. It demonstrates how definitions of sameness and difference affect physical laws, and how thermodynamics connects to questions about knowledge, identity, and the limits of observation. Maxwell's demon. In 1867, physicist James Clerk Maxwell imagined a tiny, intelligent being controlling a trap door between two chambers of gas. By letting only fast-moving molecules pass one way and slow-moving molecules pass the other, the demon could separate hot gas from cold without expending energy. The result would be a temperature difference that could power a machine, seemingly violating the second law of thermodynamics, which states that entropy in an isolated system always increases. The paradox is that the demon appears to create order from disorder, reducing entropy without cost. If true, it would overturn one of the most fundamental principles of physics. For decades, scientists debated whether such a being, even hypothetical, could exist without contradiction. Later analysis suggested that the paradox does not destroy thermodynamics, but shifts the problem to information. To sort molecules, the demon must observe and record data. Processing and erasing this information requires energy, which restores the balance. In other words, entropy is not only about matter and heat, but also about information. This insight connected physics to computation. It showed that knowledge has physical consequences, and that information processing obeys the same thermodynamic limits as machines. Today, Maxwell's demon is studied not as a literal creature, but as a symbol of the deep link between energy, entropy, and information theory. The Maxwell's demon paradox remains important because it illustrates how even the most solid scientific laws can be challenged by thought experiments. It reveals that the boundary between order and disorder depends not only on physical processes, but also on the act of measurement and the cost of knowing. Coastline paradox. In geography, measuring the length of a coastline seems like a straightforward task, yet the result depends heavily on the scale of measurement. Using a map with long measuring sticks, the coastline appears shorter because small bays and curves are skipped. Using shorter sticks reveals more detail, adding distance. As the unit of measurement shrinks, the length increases without limit. This is the coastline paradox. The true length of a coastline is undefined. Unlike smooth shapes, coastlines are irregular and fractal-like. At every level of magnification, new features appear: rocks, coves, cracks, each adding to the total distance. No matter how fine the measurement, smaller structures remain, suggesting the length can grow infinitely. The paradox reveals the gap between geometry and nature. Classical geometry assumes smooth lines, but coastlines behave like fractals, shapes with complexity at every scale. Mathematician Benoit Mandelbrot later used this insight to develop fractal geometry, showing how natural forms like mountains, clouds, and rivers resist description by traditional measures. The coastline paradox also illustrates practical challenges. Countries may dispute territory based on how coastlines are measured. In science, estimating the surface area of irregular objects, from landscapes to molecules, faces the same difficulty. The coastline paradox shows that some features of the natural world cannot be captured by simple numbers. It highlights the need for new mathematical tools to describe complexity and demonstrates how infinity can emerge not from the vast, but from the endlessly detailed. Zeno's paradox, Achilles and the tortoise. In ancient Greece, the philosopher Zeno of Elea proposed a series of paradoxes to challenge ideas of motion and continuity. One of the most famous describes a race between Achilles, the swift hero, and a slow-moving tortoise. To make the contest fair, the tortoise is given a head start. Zeno argued that Achilles could never overtake it. By the time Achilles reaches the tortoise's starting point, the tortoise has moved a little farther ahead. When Achilles reaches that new point, the tortoise has advanced again. This process repeats infinitely. Every time Achilles arrives at where the tortoise was, the tortoise is still slightly ahead. The gap becomes smaller and smaller, but never seems to vanish. The paradox lies in how infinity is handled. The race can be divided into an infinite sequence of steps. If completing infinitely many tasks is impossible, Achilles should never pass the tortoise. Yet in reality, he does so quickly. Mathematics later resolved the puzzle through the concept of converging series. The infinite sequence of steps adds up to a finite distance, which Achilles covers in finite time. The tortoise's lead shrinks to zero, but the paradox remains philosophically powerful because it shows how ordinary ideas like motion conceal deep questions about infinity and division. Achilles and the tortoise illustrates how intuition can falter when faced with infinite processes. It is less about running and more about the nature of space, time, and continuity, problems that continue to shape mathematics and physics centuries after Zeno first described them. Zeno's paradox dichotomy. Zeno of Elea described another puzzle about motion known as the dichotomy paradox. It begins with a simple task: to walk across a room. Before reaching the end, you must first reach the halfway point. Before reaching halfway, you must reach a quarter of the way. Before that, 1/8. The journey can be divided into an infinite series of smaller and smaller steps. The paradox claims that motion is impossible because completing an infinite number of steps cannot be done in a finite time. If the path is endlessly divisible, then every act of movement requires finishing infinitely many tasks, and yet in reality people cross rooms every day. Mathematics later addressed this problem through the idea of converging series. The distances, half, a quarter, an eighth, and so on, add up not to infinity, but to a finite total. The sum of all steps is equal to the full length of the journey, and it can be completed in finite time. Still, the dichotomy paradox has lasting significance. It shows how the concept of infinity unsettles ordinary reasoning. Motion feels continuous, but analysis breaks it into infinite pieces, where logic seems to halt. The paradox reveals a gap between experience and mathematics, between what is seen and what is reasoned. Modern physics carries echoes of Zeno's insight. Questions remain about whether space and time are continuous or made of indivisible units. If the universe is truly continuous, then infinite division is real. If it is not, then Zeno's reasoning might fail at the smallest scales. The dichotomy paradox continues to be studied not because it stops Achilles or ordinary walkers, but because it forces us to ask what motion, space, and time really are, and whether infinity exists in the world or only in the mind. Carroll's What the Tortoise Said to Achilles. In 1895, the writer and logician Lewis Carroll published a short dialogue between Achilles and a tortoise, meant as a playful but serious challenge to the foundations of logic. The tortoise asks Achilles to accept two premises. If A is true, and if A implies B, then B must be true. Achilles agrees, but the tortoise refuses to accept B unless Achilles also accepts an additional statement. If A and A implies B are true, then B must follow. Achilles concedes and writes it down, but the tortoise demands yet another premise to justify why that step should also be accepted. This process continues endlessly, with the tortoise always asking for one more link. No matter how many premises Achilles adds, the tortoise claims it is not enough. The paradox illustrates a problem of infinite regress in logic. Deduction relies on rules that cannot themselves be endlessly justified by further rules, or the chain would never end. At some point, the system must simply accept logical inference as a basic principle, without demanding further proof. Carroll's dialogue highlights the difference between knowing the rules of reasoning and applying them. Achilles understands the logic, but the tortoise's stubbornness reveals that reasoning requires more than formal statements. It requires acceptance of inference as valid in itself. Philosophers and logicians still discuss the implications. Some see it as a limit of formal logic, showing that rules alone cannot capture the act of reasoning. Others view it as a reminder that any logical system must rest on unprovable foundations, axioms that are taken as given. What the tortoise said to Achilles remains a concise demonstration of how even simple logic can unravel if pushed too far. It reminds us that reason has limits, and that the foundations of deduction, though rarely questioned, cannot be proven by logic alone. Preface Paradox. The preface paradox comes from everyday life rather than physics or mathematics. Imagine an author finishing a book. In the preface, they might write, "I am sure some errors remain in this book." At the same time, in every chapter, the author presents claims as true, having checked them carefully. The author thus believes each statement individually, while also believing that at least one of them must be wrong. The paradox is that both positions seem rational. It would be arrogant for the author to believe the book is flawless, yet it would be inconsistent to believe every statement while also believing that at least one statement is false. Logic demands consistency, but human reasoning accepts both views at once. This puzzle illustrates a broader problem: how to reconcile fallibility with confidence. People often hold beliefs they know might contain mistakes, whether in science, history, or daily judgment. To proceed, they must act as though individual claims are correct, while admitting that their entire collection of beliefs cannot be perfect. Philosophers use the preface paradox to explore the nature of rational belief. One approach says the author is inconsistent, and rationality requires abandoning either the global doubt or the local confidence. Another approach argues that the two attitudes serve different roles. Local belief guides action, while global doubt acknowledges human limitations. The paradox also connects to science as a whole. Researchers trust their findings enough to publish them, yet science advances precisely because errors are expected and corrected over time. Knowledge moves forward through a balance of conviction and humility. The preface paradox remains important because it captures attention at the core of rational thought. It shows how belief is not simply about truth, but about managing uncertainty, trusting claims enough to use them while recognizing that human knowledge, taken as a whole, is never beyond error. Blue-eyed Islander's Paradox. This thought experiment begins with an isolated island whose people follow a strict rule. If someone learns they have blue eyes, they must leave the island at midnight. No one is allowed to talk about eye color, and there are no mirrors or reflections, so individuals cannot know their own. They can, however, see the eyes of everyone else. One day, a visitor makes an announcement. At least one of you has blue eyes. Everyone on the island hears this. From that moment, a chain of logical reasoning begins. If only one person has blue eyes, they look around, see no others with that trait, and realize the statement must apply to them. They leave the next night. If two people have blue eyes, each sees only one other. They both expect that individual to leave after one night. When no one leaves, each realizes that their assumption was wrong. They must also have blue eyes. On the second night, both depart. This pattern continues. If there are n blue-eyed people, none leave for the first n-1 nights. On the nth night, all of them leave at once. The paradox is that everyone already knew there were blue-eyed individuals before the announcement, but the visitor's statement created common knowledge. It made the fact public in a way that changed reasoning. The puzzle shows how information works differently when it is shared, known to be shared, and known to be known by all. The rule did not change, nor did the people's eyesight. Only the structure of knowledge shifted, and that was enough to trigger a precise and dramatic outcome. The Blue-Eyed Islander's Paradox demonstrates how logic, communication, and common knowledge interact in surprising ways. It reveals that sometimes the smallest piece of new information is not about the world itself, but about what people know that others know, and that difference can transform behavior entirely. Moore's Paradox. This puzzle, first noted by philosopher G.E. Moore in the 20th century, involves statements that seem absurd, even though they are not logically contradictory. The classic example is the sentence, "It is raining, but I don't believe it is raining." Each part of the sentence could, in principle, be true. It might actually be raining, and the speaker might genuinely not believe it. Yet when combined, the statement feels impossible to assert sincerely. The paradox lies in the clash between truth and belief. Logic allows the two clauses to coexist, but communication and psychology do not. To say something out loud is to present it as something you believe. So, a speaker who says, "I don't believe it is raining," while also reporting rain, cancels the credibility of their own words. This problem extends beyond weather. Sentences like, "I ate lunch, but I don't believe I did," or "That's true, but I don't believe it," are all structurally the same. They highlight a gap between the formal rules of logic and the practical rules of assertion. Philosophers have debated what Moore's paradox reveals. Some say it shows that speech acts carry commitments beyond simple truth values. To assert something is also to claim belief in it. Others argue it demonstrates limits of self-knowledge, since people cannot always separate their beliefs from their statements about reality. The paradox also connects to epistemology, the study of knowledge. It raises questions about what it means to believe, to know, and to speak sincerely. Even if the words themselves are consistent, the act of uttering them undermines their possibility. Moore's paradox remains important because it reveals a hidden rule of communication. Truth is not enough. To speak coherently, statements must align with belief, and the failure of that alignment creates a paradoxical form of nonsense. Sentences that are logically possible but humanly unutterable. Goodman's new riddle of induction. In 1955, philosopher Nelson Goodman introduced a puzzle that challenges how humans make predictions about the future. It builds on the classic problem of induction. How can we justify the belief that patterns observed in the past will continue? For example, if the sun has risen every day, we expect it to rise tomorrow. Goodman complicated this by inventing a new concept, the property of being grue. An object is defined as grue if it has been observed before a certain date and is green, or if it is first observed after that date and is blue. By this definition, emeralds we have seen so far are green, but they are also grue. If we use past observations to predict the future, logic supports both conclusions. All future emeralds will be green, and all future emeralds will be grue. Yet these two predictions contradict each other. Emeralds cannot be both entirely green and entirely blue after the same date. The paradox lies in why green seems like a natural, reliable property, while grue does not, even though both are equally supported by evidence. Goodman argued that the problem is not with induction itself, but with the concepts we choose to project into the future. Some properties, like green, feel entrenched by language and practice, while others, like grue, do not. But this distinction is psychological and cultural, not purely logical. The new riddle of induction remains influential because it questions the foundations of scientific reasoning. If evidence alone cannot tell us which generalizations are valid, then the trust we place in prediction relies on assumptions about which concepts are natural and which are not. Goodman's challenge highlights a deep tension. Science depends on induction, yet induction cannot be justified by observation alone. The riddle shows that our confidence in the future is shaped not just by logic and evidence, but by the frameworks of language and thought that filter what counts as a reasonable projection. Meno's paradox. In one of Plato's dialogues, Socrates and Meno discuss the nature of knowledge, leading to a puzzle now called Meno's paradox. Meno asks how learning is possible at all. If you already know something, then there is no need to learn it. But if you do not know it, then you would not recognize it even if you found it. Either way, the search for knowledge seems impossible. The paradox turns on the tension between ignorance and recognition. To inquire, you must know what you are looking for, but knowing it already cancels the need for inquiry. Without prior knowledge, the search appears blind. With knowledge, it is unnecessary. Socrates answers by proposing the theory of recollection. He suggests that the soul already contains knowledge from before birth, and what we call learning is actually remembering. To demonstrate, he questions a slave boy who, through guided reasoning, reconstructs a geometrical truth he had never been taught. For Socrates, this shows that inquiry is possible because the mind already holds the seeds of knowledge. Modern interpretations treat the paradox differently. Some see it as highlighting the role of definitions. To investigate a concept, one must have at least a partial idea of it. Others argue it exposes the difference between complete ignorance and partial knowledge. We rarely start from nothing, but from vague intuitions that can be refined. The paradox remains relevant because it touches on education and discovery. How do people recognize new truths when they first encounter them? What makes learning possible if it is neither pure ignorance nor complete knowledge? Meno's paradox endures as a reminder that knowledge is not just a collection of facts, but a process of bridging the gap between the unknown and the known, a process that seems impossible in theory, yet happens constantly in practice. Banach-Tarski paradox. The Banach-Tarski paradox, discovered in the early 20th century by mathematicians Stefan Banach and Alfred Tarski, is one of the strangest results in set theory and geometry. It states that a solid ball in three-dimensional space can be cut into a finite number of pieces, and then, using only rotations and translations without stretching, those pieces can be reassembled into two balls, each identical in size to the original. At first, this seems like an impossible violation of physical laws. How can one ball become two without adding matter or shrinking pieces? The key is that the pieces are not ordinary chunks of matter, but highly abstract sets of points, defined using the axiom of choice in set theory. These pieces are so fragmented that they cannot be measured in the usual sense of volume. Because of this, the normal rules of geometry and measure do not apply to them. The paradox highlights a divide between pure mathematics and physical reality. In mathematics, space is treated as infinitely divisible, and the axiom of choice allows the construction of such bizarre sets. In the physical world, atoms and quantum limits prevent this kind of manipulation, so the paradox cannot be carried out with actual objects. Still, the result is deeply significant. It shows that some basic assumptions about infinity and measure lead to counterintuitive outcomes. It also demonstrates the surprising power and potential strangeness of the axiom of choice, which enables the existence of non-measurable sets. The Banach-Tarski paradox is not about breaking physics, but about exploring the boundaries of mathematics. It reveals how the abstract world of sets and infinity can produce results that seem absurd, yet remain logically consistent within the framework of modern mathematics. Olbers' paradox, dark night sky. In the early 19th century, the German astronomer Heinrich Olbers posed a question that seems obvious but carries deep consequences. Why is the night sky dark? If the universe is infinite, eternal, and filled uniformly with stars, then in every direction our line of sight should eventually end at the surface of a star. The sky should blaze with light, as bright as the surface of the sun, yet what we see is mostly darkness. This contradiction became known as Olbers' paradox. If the universe had always existed and stretched on without limit, there would be no dark spaces between stars. Every patch of the sky would shine. The fact that it does not suggest that at least one of these assumptions, infinite size, eternal age, or uniform distribution, must be wrong. Modern cosmology resolves the paradox by showing that the universe is not static and eternal. It has a finite age, around 13.8 billion years, so light from the most distant regions has not yet had time to reach us. The universe is also expanding, which stretches starlight into longer wavelengths, reducing its brightness and shifting much of it into invisible ranges such as infrared and microwave. The paradox is more than a curiosity. It helps shape the realization that the universe has a history, that it began in a finite past and evolves over time. The darkness of the night sky is not an absence, but evidence of cosmic expansion and the finite speed of light. Olbers's paradox remains a striking example of how a simple observation, the dark sky overhead, leads to profound insights about cosmology, time, and the structure of the universe. It shows that even ordinary experiences can reveal hidden truths about the deepest laws of nature. Allais paradox. In the 1950s, French economist Maurice Allais designed a set of choices to test how people handle risk. The experiment asked participants to choose between lotteries with different probabilities and payouts. The results revealed a contradiction between the predictions of expected utility theory, the standard model of rational decision-making, and the way people actually behave. In one choice, most people prefer a guaranteed moderate reward over a risky gamble with a slightly higher expected value. But in another choice, when both options involve risk, the same people reverse their preferences, favoring the gamble instead. These inconsistent decisions violate the logical rules of utility theory, which assumes preferences should stay consistent across similar situations. The paradox highlights the role of certainty. People place disproportionate value on guaranteed outcomes compared to merely probable ones, even when the math suggests otherwise. This certainty effect causes shifts in preference that look irrational under strict theory but feel natural to human psychology. The Allais paradox became a cornerstone in the study of behavioral economics. It showed that models assuming purely rational agents could not fully explain real-world choices. Later research, such as Daniel Kahneman and Amos Tversky's prospect theory, built on these insights, emphasizing how people perceive gains, losses, and probabilities in biased ways. The paradox remains important because it challenges the assumption that rationality is simply about maximizing expected value. It demonstrates that human decision-making is shaped by psychological factors like risk perception, loss aversion, and the weight given to certainty. The Allais paradox continues to serve as a reminder that human reasoning often departs from strict logic, and that understanding real choices requires blending mathematics with psychology. Ellsberg paradox. Proposed by economist Daniel Ellsberg in 1961, this paradox challenges traditional models of rational choice under uncertainty. It highlights how people react differently to situations involving known risks versus unknown probabilities. The classic setup involves two urns filled with red and black balls. From the first urn, you know there are exactly 50 red and 50 black. From the second urn, the mix of colors is unknown. If asked to bet on drawing a red ball, most people choose the first urn, even though both offer the same minimum chance. When asked to bet on black, they again choose the first urn. This reveals a consistent preference for known risks over ambiguous ones. The paradox lies in the contradiction. If people were purely rational according to expected utility theory, their choices should not systematically favor one urn, since the unknown urn could have any distribution, including one that is more favorable. Yet most consistently avoid the ambiguous option, displaying what is called ambiguity aversion. Ellsberg's finding was influential because it showed that classical economic theory did not fully capture human behavior. People care not just about probabilities, but about how much they trust those probabilities. Known risks feel safer than unknown ones, even if the outcomes are mathematically equivalent. The paradox has wide applications. It helps explain why investors prefer familiar markets, why policymakers struggle with uncertain data, and why people often avoid choices involving incomplete information. It also sparked new models of decision-making, such as prospect theory and models of ambiguity aversion, which better reflect how people actually think about uncertainty. The Ellsberg paradox demonstrates that uncertainty is not just about numbers, but about psychology. It shows how human decision-making departs from strict rationality, favoring the comfort of the known, even when the unknown could offer equal or greater reward. Paradox of thrift. The paradox of thrift, introduced by economist John Maynard Keynes, describes how an action that is wise for an individual can become harmful when practiced by society as a whole. Saving money is generally seen as prudent. It provides security and builds resources for the future. But if everyone increases their savings at the same time, total spending falls, and the economy can slow down. When demand drops, businesses sell less, reduce production, and cut jobs. Incomes decline, making it harder for people to save. What began as an attempt to strengthen personal finances ends up weakening the overall economy, leaving individuals no better off and sometimes worse. The paradox highlights the difference between microeconomics and macroeconomics. At the individual level, thrift looks rational. At the collective level, it can create a downward spiral of reduced spending and lower growth. The contradiction lies in the fact that what is good for one may not be good for all. Economists debate the scope of this effect. Some argue it applies mainly during recessions, when consumer demand is already weak. Others see it as a broader principle showing that economies need a balance between saving and spending. Too little saving leaves no room for investment. Too much saving stalls economic activity. The paradox of thrift remains influential in discussions of fiscal policy and economic crises. It shows why governments sometimes encourage spending during downturns, even if saving seems like the safer choice. Ultimately, the paradox demonstrates that individual rationality does not always scale up to collective benefit. It reveals the tension between personal caution and societal prosperity, and the fragile balance that keeps economies stable. Sunk cost paradox. The sunk cost paradox arises when people continue a course of action not because it makes sense in the present, but because they have already invested time, money, or effort in it. Rational decision-making says past costs should not influence current choices. Only future benefits and costs matter. Yet in practice, humans often feel compelled to get their money's worth, even when continuing only deepens the loss. A common example is staying through a bad movie because you already paid for the ticket. The money is gone whether you leave or not, but many people sit through the film to justify the expense. In business, companies sometimes keep funding failing projects because of the vast resources already committed, fearing that stopping would make those investments wasted. The paradox lies in the contradiction between logic and psychology. Rationally, past costs should be ignored, yet emotions and social pressures make them hard to set aside. People dislike admitting loss, and they value consistency, so abandoning an investment feels worse than continuing, even if continuing is harmful. This behavior connects to deeper cognitive biases. Loss aversion makes people more sensitive to losses than to gains. Commitment bias pushes them to stick with past decisions. Together, these forces create a powerful pull toward honoring sunk costs, even when doing so is irrational. The sunk cost paradox is more than a curiosity. It explains personal decisions, such as persisting in unfulfilling relationships or hobbies, and large-scale failures, such as governments prolonging costly projects. Recognizing it can help individuals and organizations make clearer choices by focusing only on future outcomes. The sunk cost paradox demonstrates how human reasoning departs from strict rationality. It shows that the past, though logically irrelevant, continues to shape decisions, binding people to paths they would abandon if they judge them only by what lies ahead. Privacy paradox. The privacy paradox describes the gap between what people say about valuing their privacy and how they actually behave. In surveys, most individuals insist that personal data is important to them and should be protected. Yet in practice, the same people often give away large amounts of information online in exchange for convenience, entertainment, or small rewards. Examples are everywhere. Users agree to detailed terms and conditions without reading them, allow apps to track their location for minor features, or share personal details on social media despite claiming to care about confidentiality. When faced with the immediate benefit of access or speed, long-term privacy concerns are often set aside. The paradox lies in the contradiction between stated values and observed actions. People express strong concern, but their choices suggest that privacy is negotiable, or at least less important in the moment. Some researchers argue this is not hypocrisy but the result of complex trade-offs. Individuals lack clear information about risks, underestimate future harm, or feel powerless to control data collection. Economists and psychologists use the privacy paradox to study how people handle uncertainty, trust, and invisible costs. It also raises questions about responsibility. If individuals consistently undervalue their privacy, should protection depend on personal choice, or should it be safeguarded by regulations and technology? The paradox remains relevant as digital systems expand. It illustrates how human behavior can diverge from stated principles, and how abstract values like privacy become fragile when placed against immediate, tangible benefits. The privacy paradox is not only about personal data, it reflects a broader theme. People often act against their own declared priorities, revealing the tension between what we believe in theory and how we behave in practice. Knowledge-confidence paradox. The knowledge-confidence paradox describes a curious imbalance between how much people know and how confident they feel about what they know. In many cases, those with limited knowledge display strong certainty, while those with deeper expertise express more hesitation. The paradox is visible in everyday life. A beginner learning a subject may feel they understand it fully after grasping the basics, confidently offering opinions and advice. Meanwhile, experts who are aware of complexities and uncertainties often qualify their statements and appear less sure, even though their understanding is far greater. Psychologists link this effect to what is sometimes called the Dunning-Kruger effect. Ignorance can create an illusion of mastery, while knowledge exposes the depth of one's own limitations. The more you learn, the more aware you become of what remains unknown. Confidence falls even as true competence rises. The paradox matters because confidence influences trust. In conversations, workplaces, or politics, people often believe the most certain voices, even if they are the least informed. Those with genuine expertise may be overlooked precisely because they refuse to claim absolute certainty. The knowledge-confidence paradox raises questions about how societies should value information. Should confidence itself be treated with suspicion? How can groups ensure that knowledge, not just certainty, guides decisions? The paradox remains a reminder of the fragile relationship between truth and belief. It shows that the loudest voice is not always the most accurate, and that wisdom often appears in the form of caution rather than certainty. Philosophical zombie paradox. This paradox comes from philosophy of mind and asks whether consciousness is necessary for behavior. Imagine a being that looks and acts exactly like a human. It speaks, moves, and responds in every way a person would. But inside, there is no subjective experience, no inner awareness, no feeling of what it is like to exist. This being is called a philosophical zombie. The paradox lies in whether such creatures are possible. If they can exist, then consciousness is not required to explain behavior, because all actions and words could be produced without it. That conclusion threatens the idea that subjective experience plays any causal role in the world. Some philosophers argue that zombies are impossible because consciousness is tied to the physical processes of the brain. If the processes are identical to a human's, then the experience must also be identical. Others defend the thought experiment as logically coherent, showing that physical explanations may never capture the reality of subjective awareness. The zombie idea is not about monsters, but about the mystery of mind. It highlights the hard problem of consciousness, why brain activity should give rise to inner experience at all, instead of functioning in silence. The philosophical zombie paradox remains unresolved. It is a way of testing whether explanations of the mind can account not just for outward behavior, but also for the private world each person feels within.